Everyone. Welcome to the speakers and the audience. My name is Clement Fortin, and I'm doing research on PLM and system design and MBSE for quite some time. And it's a real pleasure for me to be here and share this session. I will introduce each speaker briefly before the talk, and then Robert will start the presentation and the video presentation. And of course, our second paper there won the jury selection. So congratulations to Atif and Stephan there. And we're really looking forward to our presentation during this session. I think we have a number of excellent papers there. So we will start right away. Let me introduce Julian briefly. So Julian Stumpf there studied mechanical engineering at the bachelor program at the University of Applied Science or Ravensburg, Weingarten, and where he focused on simulation and design of mechanical system. And since 2018, Julian has been a PhD candidate at the Mercedes-Benz AG in collaboration with the Laboratory for Product Development and Lightweight Design at TUM. His recent research focuses on robust design and mechanical systems in early development phases. So we can start the presentation.
Hello, everybody. My name is Julian Stumpf. I am PhD candidate at Mercedes-Benz in collaboration with the Laboratory for Product Development and Lightweight Design at the Technical University of Munich. Today, I'm glad to present our paper, Systems Design Using Solution Compensation Spaces with Built-in Tolerance Applied to Powertrain Integration. First of all, I will quickly explain the motivation of this paper. Then I will explain something about the methodology. Afterwards, the application to a powertrain mount system, and at the end, the results with conclusion and a quick outlook. When we look at the integration of a powertrain system, the increasing number of components in hybrid vehicle architectures leads to lack of space in the front part of the vehicle. And at the same time, the requirements for noise, vibration, and harshness criteria get increasingly important. For example, a soft start of the combustion engine while driving. Both on the left side, the more geometric requirements, and on the right side, the functional requirements depend on crucial design variables, in this case, the positions of powertrain mounts. In general, there are often iteration loops in the design process to meet all geometric and functional requirements. The idea of this paper is to project the flexibility of uncritical and easy adjustable design variables, in this case the stiffnesses of engine mounts, onto the crucial design variables, in this case the mount positions, to accelerate the design process. Let's now have a look at the solution-based engineering approach and different projection methods. Therefore, we look at the two-dimensional design space with the variables XA and XB, a linear constraint complete solution space that is called omega C, and every design within this green space is a good design, which means every system requirement is met. The maximum solution box that completely decouples all design variables is called omega. Let's now assume that XA is called an early decision variable, for example, the position of an engine mount that needs to be defined in an early stage of development process and is very crucial to the development process. In contrast, XB is called late decision variables, for example, the stiffness of an engine mount. This variable can be adjusted in a later stage of development process. Therefore, we first want to define or find solution spaces only for XA. The projection of the conventional solution box is very small, this interval. Therefore, the idea is to completely project the complete solution space onto the early decision variables. This is called omega ASCS for solution compensation spaces. Once the early decision variable is defined, then the late decision variable can be set that the design point at the end is inside of the complete solution space. But if an early design is chosen at the corner of the complete solution space, there may be too less tolerance for the late decision variables. That's why there is a new definition, so-called solution compensation spaces with built-in tolerance, that only project the solution space that ensures enough flexibility for the later design of the system. I now present the XB-linear algorithm to calculate solution compensation spaces with built-in tolerance. This algorithm can treat problems that are linear with respect to the late decision variables. To explain it, we look at the 4-dimensional problem, 2-dimension in the early decision design space and 2-dimension in the late decision design space. The outer optimization problem takes place in the early decision design space with the Monte Carlo sampling technique. For each sample point, the calculation of the solution of a linear program is necessary to check if there is a good late decision design with enough tolerance. This is shown here. Given is a minimum tolerance for the late decision variables, and if there is a box that is bigger than this tolerance, this is the tolerance flexibility is enough, and the early design is a good design. If this box would not fit inside of the late decision solution space, this sample point would be not good. Let's have a look at the results of the design of a powertrain mount system. The early decision design space consists of all position information of the mounts. Each sample point represents an early decision design, and the colors indicate if there is a late decision design, the stiffnesses of the mounts, with enough tolerance. And that means the complexity of the whole system is projected onto the early decision variables. What this means is shown here. When we choose one design point, we can project into the late decision design space and see that there is a box with sufficient tolerance for the stiffnesses of the mount. We can also choose another early decision design, and we will see that there's a completely other solution space for the late design, but as well as for the first one, enough flexibility. When we compare the different late decision design spaces of two different early designs, we see that they are completely different. That means with the picture on the left, you cannot say how the stiffnesses of the mounts need to look like, but you can be sure that there is a solution that offers enough flexibility. Let's come to a conclusion. We presented an approach to project solution spaces onto the crucial design variables of a problem and an algorithm to calculate those projections. We could apply this to the design of a powertrain mount system and show that the resulted solution boxes got larger and thus more flexibility in the positioning process of engine mounts could gain. Since the algorithm only works for systems that are linear with respect to the late decision variables, to expand the field of application, the future work should contain research into efficient algorithms for nonlinear systems. That's from my side. Thank you for your attention, and I'm happy to answer your questions.
Thank you very much, Julian. We will wait for questions at the end and exchange at the end. We will now go to the second presentation, and I will introduce two participants there. I will first introduce Atif, who did the video, and but he cannot be at the conference. So Dr. Engineer Atif Mahboob is a postdoctoral researcher at the Technical University of Ilmenau in Germany. And in 2020, Dr. Mahboob defended a PhD thesis that focused on the use of SysML behavior models for achieving dynamic use cases of technical products in different VR systems. Professor Stephan Husung will also be answering questions at the end. And Professor Husung is the head of the product and system engineering group at the Technical University of Ilmenau. So welcome, and Atif, and we will start the video.
My name is Atif Mahboob, and I welcome you all to our talk about a modeling method for describing and facilitating the use of SysML models during design process. I would be presenting the core content of the research paper briefly inside this video, and your questions will be taken by Professor Stephan Husung during the design conference. My talk will consist of the motivation, the research questions, followed by a brief overview of state of art, the modeling approach, and I will finally reflect upon the results. Our motivation here is to reuse SysML models of components of a product in further products or in further developments. In other words, we want to reuse the already available SysML models. When we talk about the reuse, we can have two different reuse situations. So in one situation, we can have a reuse case of system 1 and system 2 having a subsystem 1.1. So subsystem 1.1 that was mainly developed inside the description of system 1 can then be reused during the development of system 2 as well. Subsystem 1.1 description may well also have different variants inside modeled inside its description. Or in another situation, we can have parallel development of different systems. For instance, here we have system N and system M, and both of these systems have subsystem that can be fully substituted or completely substituted with the description that is already available in the form of subsystem 1.1. Secondly, when we talk about such a reuse, it is important to integrate the top-down system descriptions with the bottom-up subsystem descriptions. For instance, we can have a look at this diagram. From top-down, we obtain system descriptions that are required in a certain development cycle. From that, we derive the subsystem descriptions, and we may have a subsystem description we call is description that are already available from some previous development. Now, at this point, it is important to integrate the top-down system description with the bottom-up system descriptions that are already available. Furthermore, we focus toward modeling and management of variant of this subsystem so that such a reuse can be facilitated. We look at three main research questions, where the first question is how these bottom-up descriptions of subsystem can be modeled in MBSC that match the required top-down descriptions where they will be reused later, or where they can be reused later. How can the system description or some part of these descriptions can be reused while keeping the remodeling effort as minimum as possible? Also, how can we play around, or how can we deal with different model variants? How can these variants be built or described in such a way that they are on one side consistent with required specification, on the other side they can be reused as well. Looking at the state of the art, we can have I look at the generalization concept relationship inside SysML, talking about variance and reuse situation. Currently in SysML, the generalized relationship is used, where then through redefinition of ports and different variables, certain aspects of the parent systems are redefined inside a certain variant, and then they can as well be used while describing the behavior of one particular variant. However, this leads to a problem if we want to reuse this variant. Reusing this variant in an environment where the parent specification is not available will lead to broken linkages. All those elements that were redefined from the parents will have broken linkages, and if we have a deeper look, these broken chains or broken linkages will also be visible inside the behavior model because the same variables were used inside there as well. So in order to tackle this problem, we have looked towards the use of redefined variables and ports, as well as local definition of these variables and ports. Let's say we have here a high-level solution architecture, and first we redefined the ports that were available on the parent system inside a certain variant, and we have also the variables from the parent inside that particular variant shown here in orange. But a crucial point here is that we create the reports as well as the variables with the same specification locally as well. And then we first link the inherited elements with the locally created elements. And moving on from here, inside the behavior description, we use then the locally created elements. This can then avoid the broken linkages problem. For instance, if this variant 1 will be used somewhere where the parent system is not available, then the remodeling effort will require just a redefinition and linking of these variable with local variables. The same idea can be used further. We did not only look at these few elements like generalization, ports, and variables. We also look beyond these elements, and the overview of the scope of these elements is available inside our research paper. I invite you all to have a brief look at this at our research paper as well. To summarize our result, we have presented a modeling method for facilitating the reuse of SysML models of subsystem and their variants in multiple systems. We clarified the scope of individual SysML elements for this reuse, and we talked about the integration of subsystem descriptions and its variant in the with that of top-down descriptions in a current system development. At this point, the scope of use of signals is not quite clear, and it can still build direct dependencies, so it has to be further refined, and in future we'll look at this. Furthermore, we plan to include further SysML elements inside the discussion to evaluate their effect on the reuse of SysML descriptions and to ponder on the implication of this particular use case, this particular reuse. This was all from my side. Thank you very much.
Thank you very much, Atif and Stephan. And I encourage you to I see that there's starting to have some questions in the chat. I encourage you to include some more, so please go ahead. And while we're going to the third presentation, I will introduce the speaker. So our third speaker is Lukas Schwan, and he's born in Germany. He studied mechanical engineering, and afterward he started his master's studies in automotive and mechatronics at the University of Bayreuth, which he successfully completed in 2020. And then since 2020, he has been working as a research assistant at the Institute of Product Development and Mechanical Engineering Design under the direction of Professor Dr. Engineer Dieter Krause at the Hamburg University of Technology. So Lukas, we are looking forward to look at your video presentation. Thank you.
Hello, my name is Lukas Schwan, and I'm a PhD student at the Institute of Product Development and Mechanical Engineering Design at the Hamburg University of Technology, and I'm happy to present the results of our contribution.
First, I'd like to start with the background and the motivation. And we are in the aircraft cabin, which faces different challenges in the area of product development. So on the one hand, there's a high number of different variants in the cabin, which need to be reduced on one hand. And on the other hand, the weight also plays an important role to save mass and fossil fuels, for example. Solutions already exist for both of the challenges. For example, with the help of suitable modularization methods, internal variety can be reduced while maintaining also the external variety. Lightweight design also can be used to further reduce weight. However, if we now look at the effects of the two disciplines, we see that modularization can reduce complexity costs, for example, but weight also increases due to the standardization of interfaces, for example. And in the area of lightweight design, the weight can be reduced, but the cost can increase. So overall, we see that there's a conflict in terms of the goals and also the effects of the two disciplines. Now, In order to unite these partly conflicting goals, modular lightweight design has been established, and it's an approach which the two areas are carried out parallelly. For this purpose, also a product model and also a process model, which can be seen at the bottom of this picture, have been created in past research. If all steps are completed, the result is a modular hybrid design that represents a compromise between modularization and lightweight design optimization. Okay, we now look at the models which are used in the two disciplines. On the one hand, we have system models which are used in the area of modularization, and in the area of lightweight design optimization, we have FE models which are used. And a major problem in the unification of these two models is that a constant data exchange between the two models is not possible because there's a lack of a suitable interface here. Therefore, we have created a methodical procedure in this contribution. When a first step, it must be analyzed which data the FE models need at all. Afterwards, it's necessary to define corresponding data types. The third step, the data structure and the data flow are now defined, and the starting points are the system model and the FE models. And in the system model now contains data on the corresponding product variants and also on the different components which are included. And the data is now further processed and transferred in the FE model, and with the help of different references or these from the system model, it's now possible to access an external FE database which meshed component models are stored, for example, and also material data as well. Afterwards, the calculation can be performed, and the results are then transferred back to the system model. So in the first step, we also need some exchange formats for the data exchange. And here, JSON, for example, can be used on one side, and on the other hand, Excel can be used for the re-import of the FE results back in the system model. Finally, a concept for data configuration and preparation needs to be created. And here, we can use template files, for example, to get the data from the system model in the corresponding data format. On the other hand, we can also use mapping functions to feed the FE results back in the system model. The interface created on the basis of this methodical procedure was then implemented for the example of an aircraft cabin, and we used the Cameo system model after that. Here you can see two product variants which partly contain the same components, and furthermore, you can also see the results from the FE simulation. The exact implementation of the interface is shown below as an example. Here we have the corresponding data, for example, for the product variants, which are stored in block definition diagrams. They refer to the different components which we use, which also refer references to an FE database. And afterwards, we can translate the data in the JSON format and run our simulation, and then re-import the results back to the system model here. The interface now offers potential in the modular lightweight design, among other things. Also, to illustrate this, an example is given below with two product families and corresponding product variants. Here, the left panel is used in both of the product variants. It's now possible to optimize the two product variants individually by means of the single model optimization, which is shown in the upper image. And another possibility is to optimize this panel together for both of the product variants, which is shown in the image below. Here we can use the multi-model optimization. And now with the help of the interface, this process can be carried out even more efficiently. And in further research, a transfer of the interface for further examples from the aircraft cabin is also planned, and an application of the methodical procedure for generating interfaces for other applications is also possible.
With this, I want to close the presentation and thank you for your attention. And if you have any questions, feel free to ask.
Thank you very much for the presentation. Okay, so please ask your questions in the chat, and we can also interact live after, of course. This is totally possible. We will now move to the fourth presentation, the fourth paper by Ünal Yildirim, and I will introduce you, Ünal. I know you're there too. And Ünal received a master and PhD degrees from the University of Bradford in the UK. His research interests include automotive system engineering, design, and product development, in particular functional modeling of complex multidisciplinary systems and engineering change management. He's currently working as a lecturer at Hubei University of Automotive Technology in China. So please, we'll listen to the video, Robert, and we will go to the next one. And again, please insert your questions in the chat.
In this presentation, I am going to talk about the evolution of a function model approach introduced in an automotive company. I will start by talking about motivation and objective of our research. Then, coherent with the structure of our paper, I will be focusing on other items as you see on the slide. Many scholars highlighted the importance of function modeling in product design and development, such as understanding system. However, function modeling is not widely used in practice, despite its potential contributions. We introduced systems the flow diagram SSFT to address this gap. We did this by basing SSFT on a critical review of established function modeling approach and the guidance for its application to particular problems. In this research, we aim to evaluate the application of SSFT in terms of its application across the company and its use on projects. We also focused on the identification of the type of problems highlighted by the practitioners. We introduced SSFT in the context of fallen mode avoidance FMA framework in the company. You can see the SSFT on the left in a black dotted rectangle. Arrows show the flow of information between tools. SSFT in this context supports the integration of FMA with systems engineering design V-model to deal with fallen modes early in the design process. It also supports the deployment of other FMA tools, such as interface analysis as you see on the slide. We assess the application of the SSFT based on a list of technical reports in the company. You can see some details about this report on the slide. We focused on the analysis of the first 100 reports at two stages. At stage 1, we aimed to offer a glimpse of the SSFT usage in the company, like application level. At stage 2, we focused on a small sample of reports for a detailed analysis of SSFT usage of projects, such as the integrity of the SSFT applications. The diagram on the left represents the overall usage of SSFT across technical reports. As you see, nearly 3 out of 4 engineers use SSFT in their projects. Interface analysis consists of interface matrix and interface analysis tables. There is a direct information flow from SSFT to interface analysis and indirect information flow to boundary diagram and FMA via interface analysis. The diagram on the right represents use of subsequent FMA tools in connection with SSFT. Nearly all projects with SSFT, 70 reports, develop boundary diagram following SSFT, while over 80% of 72 reports employ interface analysis and FMA. This is an indication of a consistent application of the SSFT across the projects and consistency of information flow between the tools. The diagram at the top illustrates the analysis of the level of application for SSFT across reports. Application of the SFT at multiple system levels by 75% of the projects shows the integration of the SFT methodology with the systems engineering approach. The diagram at the bottom provides an analysis of the distribution of the number of SFT applications with the phase of product development and the samples of engineering competence in the company. Overall distribution of the SFT applications in the project is coherent with the distribution of engineering workforce in the company. At stage 2, we focus on doing a detailed analysis of the SFT usage on projects. The diagram on the left represents the application of the SFT across engineering disciplines. The diagram on the right illustrates the level of integrity in the application of the SFTs. The assessment of the integrity of the applications was carried out in line with the use of the guidelines provided to the engineers. A detailed, individual review of the selected project technical reports was carried out to analyze problems in function modeling experienced by the practitioners. You can see the top 3 problems: fork join nodes, closed loops, and nested function modeling. We also documented the strengths of the SFT highlighted by the practitioners. For example, the flow of information to other FMA tools such as FMEA, solution neutral analysis of systems, and the integration of the SSFT with the tools developed in the company. Engagement of engineers with SFT from across all engineering competence areas, phase of product development, and levels of systems shows its potential to support collaboration, comprehension, and communication. Usage of the key tools in conjunction with the SFT across the company underpins the identification of new functions, requirements, furthermore, and test cases. In the next stage, we will be focusing on the application of the SFT to closed-loop control systems, which is quite important in the development of autonomous systems. We will do some work on the validation of SFT with software architecture-driven standards. We will also be working on the evolution of the usefulness of the SFT as compared to other function modeling approaches. Thank you for listening.
Thank you very much. We'll now go to, and I don't see enough questions on the chat. I hope we're going to have some more on live exchange there, which would be great. So now we go to our last presentation by Tommy Langen, and I will introduce Tommy right now, and we can go to the last presentation of the last session of the conference. So Tommy Langen is employed at the University of Southeastern Norway as a research fellow. He holds a Master of Science in System Engineering with Industrial Economics and a Bachelor in Mechanical Engineering with Product Development. He has several years' experience from the subsea oil and gas industry, working from early concept to testing of complex systems. So currently, he's involved in a PhD research on big data in early phase system engineering, focusing on innovation and human factors. And this is what he's going to be talking to us about. So please, Tommy, the floor is yours.
Hello, and welcome to this presentation for this paper, A System Thinking Approach to Data-Driven Product Development. This study was performed by Kristin Falk, Naumann, and myself. In this presentation, I'll give you an overview of how we applied system thinking in an ongoing research project. A project that focuses on how the industry can utilize big data and digitalization in their early product development phase. The research project this paper is connected to is called HSIF, and this is its second iteration. It consists of 9 Norwegian tech supply companies that develop products such as autonomous systems, smart parking infrastructure, subsea solutions, maritime systems, and various services for clients around the world. The purpose of using system thinking in this project was to identify research directions for how the industry can utilize big data in their product development. By using system thinking approach, we got a better understanding of these companies' current states and needs. Out of this research objective, we defined 2 research questions. The first question we asked in order to find gaps within the industry in our area when it comes to data and digitalization needs. The second research question, we want to analyze the problem space to find the leverage points for future studies. We highlight 4 leverage points. 2 of them emphasized on the industry-academic research collaboration, and 2 on the research domain, which is the data-driven product development. The system thinking approach we used were based on the Boltzmann soft systems methodology, which again is based on Clement's soft system methodology, illustrated in the center of this slide, bridging the real world and the system thinking, with support from the openness diagram, CATVO, and systemogram. The initial steps, step 1 and 2, consist of meetings, interviews, workshops, and defining each company's problems and needs. With the information from the previous step, we moved into the system thinking domain, first transforming the information into structured text. We then conceptualized the structured text to better understand the system, its relation, and forces. One of those tools we used was the openness diagram. The openness diagram helped us get an overview of the various stakeholders, systems, and environment, and their area of influence, useful in relation to identify leverage points. We also used CATVO to understand and communicate the purpose of the system. It highlights the value from the various points of views, used from the customer, the actors, what to transform, the context through the worldview, and the environments. The systemogram is the heart of the approach we used here. I'll go a little bit deeper into the systemogram on the next slides. And on the last steps, we use for iteration with discussion and validation of the findings from the system thinking analysis. The final step is now ongoing research. Here you can see the systemogram that is drawn based on the study. A systemogram is a conceptual representation of a system with nodes and explanatory links that communicate behaviors. The benefit of systemogram is that it helps people think systematically about the system and understand the interrelations in the problems. The model can aid in identifying causal loops and leverage points for deciding where to emphasize modification on the system to achieve the desired goal. It can be a little overwhelming at first, but we can start with the mainstay. Mainstay, also known as mainstream, is the purpose of the system. Starting from the top left, the mainstay story reads: HF2 consists of industry partners who collaborate and share best practices used in product development processes that are verified and validated in industry cases, which has access to big data systems used with tools and methods to perform early exploration and validation to design suitable system of interest to deliver higher satisfaction to company customers. I'll now highlight 4 leverage points that we see as important for suitable research directions for achieving data-driven product development. In leverage point 1, we see the industry cases are the key elements in tying the research project and the applications domain. With industry cases, academia can support the companies having possibilities to learn and explore, and it is possible to verify and validate the suggested solutions. Therefore, it is important that the companies make available, relevant, and applicable industry as laboratory cases to the research project. Leverage point 2. The teams related to each industry case need to be motivated and have backing from their company. Additionally, academia has a supporting role in pushing the research forward. Research will add resources such as access to scientific papers and subject matter experts. They will also support by exploring and validating the possible solutions. The industry partners will collaborate and share industry best practices, while academia supports them with input from the body of knowledge. This indicates that the communication and collaboration between the companies, academia, and the industry cases are vital as it gives valuable research input. Now, number 3. A central system in HF2 project is the system of the big data, here named big data systems. It consists of data, software, infrastructure, and architecture. Big data is the source for the information and knowledge about the system of interest and their users. For the engineers, managers, and operators to make sense of the big data and perform data-driven decision, it needs to be transformed through tools and methods. A research project needs competence and capabilities to build big data systems and architectures relevant to the industry cases. In leverage point 4, we want to highlight that big data and people are the material and tools to achieve things. However, it is the interaction between the technical and the social world that gives the possibility to create value. On its right side of the systemogram, we see that the key elements to achieve this goal lie in the socio-technical domain. In this presentation, I have shown an applied system thinking approach in an ongoing industry academic research project. A project that focuses on how the industry can utilize big data and digitalization in their early product development phase. Based on system thinking analysis, we suggest 4 main leverage points for reaching that goal. Those 4 were emphasize the industry cases, the collaboration between the companies and academia, develop a big data system architecture, and maintain a socio-technical view. Thank you very much for your time.
Thank you very much. Now we're at the tummy, and we are going to go for questions and exchange, and we're looking for this. So there's already a series of questions. I've asked a few, and I've seen that Stephan has asked some and others. So well, why don't we start from the top and go down? If you so I would say here that the Julian, and Julian, if we see that your microphone, how do you determine that the relationships for the projections are linear, and how do you deal with possible uncertainties in the projection onto the solution space?
Okay, first of all, thank you for this question. In this application, we are looking at the dynamic behavior of the engine. So we have a multi-body system and looking at the global stiffness matrix. And we know that, of course, the stiffnesses, the local stiffnesses of the engine mounts are linear with to the global stiffness matrix. So we first of all define a solution space on the stiffness matrix, and then the projection technique is linear with respect to the stiffnesses itself. Yeah. So this is just a question of the model you're using in the background.
Okay. It's an assumption of your model.
Yeah.
So this means it's an assumption of your model you used for the projection.
Actually, you have the model and you have the projection itself. So the model is the bottom-up mapping. You know how your stiffness matrix looks like when you know your local stiffnesses of the mounts. And the projection technique is then an analytical actually a linear optimization problem, where you project the solution spaces onto your local stiffnesses back. And this projection technique, when we come to the second part of the question, is with less uncertainty, because if you find a linear in a linear program, if you find an optimum, it's the global optimum, and you can you don't have the uncertainties in the projection technique. But there are other sample-based projection techniques, and then you can go for probabilistic analysis as well, so that you define that you don't want to have 100% good designs in your solution box, but maybe 95% or something like that.
Okay, thank you.
And I asked a question, Julian, how do you know that you have enough tolerant space for a given design? You know, because you might have too much sometimes, but not enough some other time. How do you deal with this?
Yeah, you need to define it. It's an input for the technique, for the method, and in this case, it's the tolerance you need for the stiffnesses is due to manufacturing process and life cycle change of stiffness, and for that you can assume a number of actually it's a relative tolerance. So in normal mounts for engine, it's about plus minus 10% variance in
Okay.
manufacturing
Okay.
process.
Okay. Okay. So you start with an assumption or a well-documented historical data there. Okay.
Yeah.
Thank
Yeah.
you very much. And Yunal is asking, and maybe Yunal, if you want, you can ask the question yourself.
Yeah, I can ask. I'm sorry, I can't hear you on and off actually. I don't have a good connection. I don't know why. I am sorry about that. If I have an issue with my connection. No, it's okay, I think. Yeah? Who can hear me?
I
Yes,
can hear
yeah.
you well.
Yes, yeah, we can
That's
hear
fine.
you well.
Yes. Julian, I wanted to ask actually how you decide this upper value and lower value in your approach, or if you have any approach actually, because if you have too high, it might affect other elements. Yeah, I put some examples there. If you see on the chat window, how you decide that?
So in this method, we are projecting the functional requirements for the decision makers. That's the idea. So the decision makers, they who need to position the engine mounts, they are happy when they know in which intervals they can place the mounts. So the costs and the for example, what did you write? Interfacing components in systems are considered by the decision makers, and when they know where the functional requirements are met, you do not need to check every time they make an assumption if the system requirements on NVH criteria are met. So you don't need to make this iteration loop. Is this the answer of your question?
That's enough. I think that's quite important issue. I think this other side of the story. I think you need to think about how to decide this approval. Then okay, thank you.
Okay. Any other questions for Julian and their paper? Any other live? You can ask questions. Everything is open and fine. No, nothing for now. We'll come back to this. I have a question for the second paper. Again, congratulations on that paper, Stephan. How do you determine the broken links? Because I think this is a very interesting part of it, but and how do you do it?
Yeah, that's a good question. So currently this is done manually because if you exchange a subsystem, you have to make a new alignment or new traces between the system modeling and the subsystem modeling. So this is currently done by hand. But maybe from a methodology point of view, always if you transfer parameters, if you transfer ports, if you transfer activities or anything like this between different system levels, you make a connection between the different levels. And then you always have to make a rearrangement, a realignment, or you have to make a remodeling in some cases if you exchange the subsystem, or like in our case, if you use the same subsystem in a different system, on an overall system. So, and based on this approach, we try to decouple the system and the subsystem as possible, as much as possible. And here we always look from a methodology point of view, what is really necessary to move between the system levels and what can be, for example, here, like Atif taught in the presentation, can be redefined on the system level, and then you only have to update the redefinition, and then you have a decoupled description of the system and the subsystem element. Especially in our case at Ilmenau, we come from precision engineering, and we have to deal with a lot of sensor systems. And for example, if you want to reuse a sensor in different systems, for example, a force sensor, a movement sensor, or something like this subsystem will be reused several times. And then it's very, very important that you have a decoupled description. And based on this methodology, we try to identify what is really necessary to couple and what could be decoupled. And Atif found a very good way to do this.
Okay, very good. And are you using any method like DSM or anything like this, or matrix for analysis of the use case reuse and this type of thing? Anything like this, or you have a different approach altogether?
Yeah, currently I think we, for normal cases, we combine different methodologies. From my point of view, I like the SPACE method. I don't know if you know it. It comes from Technical University of Munich. They also work with different system levels and an independent description of different system levels. And this is a good starting point also for our way of working here. And we also combine this with well-known approaches also from the design methodologies up to
we're using you. We're losing you, Stephan. At least I am. I don't know if the others are losing you. Could you repeat the last 15, 20 seconds of your answer? I lost you.
Can you hear me now? Can you hear me now?
Yeah. Can anybody can? Yeah. It's good now. It's good.
Yes, it's better.
Better now.
We are losing you once again.
Yeah, we're losing you. Oh, we lost him. Okay, he will come back then. There is a network problem. Well, let's go to the next one then. Well, I guess it was Stephan that did. Let's wait for this. For Lukas, I ask, how can you extend your proposed method to subsystem? Now you had a component, okay, and then you're doing, of course, finite element analysis. My question is, how can you extend this type of method to another space, like a subsystem? Let's say you had an engine like we had in the first case or not a fixed component. Is that applicable, or is it pretty well linked to the finite element method and the structural analysis? Lukas.
Yeah. So within the scope of our methodic modularization, and especially in the scope of the aircraft monuments, smallest entity which we looked at is the component level. So on subsystems, we currently do not look deeper. But however, the method and also the systematic behind is very generic. So the further research, it should also be able to adapt it to subsystems.
Okay. But when you're saying at the end there, you want to extend it to other types of components which are becoming sub-assemblies at least. Is that what you're looking at? Or it's pretty well all going to be sub-assemblies, but within one part kind of thing, or one rigid set?
Yeah. What I meant is that we took the example of an aircraft partition. And what we want to do in next steps is to do to also look at bigger kind of cabin monuments, for example, galleys and so on. And there, of course, subsystems also play a big role. Yeah. And I think that's a good point. We should take that more into account in further research. Thank you.
Yeah, because galleries, of course, are subsystems. Yes. Stephan, okay, thank you very much, Lukas. Any questions for Lukas now? Any other questions? No, I don't see. Stephan, we lost you, but maybe you can come back.
Yes, sorry, I had to update. It's Thanks for going on, and thanks for the answering, Lukas. Yeah. Very important topic. Yeah.
Yeah, but Stephan, to come back to your questions there, you were explaining your methods and so on. Maybe we can come back because we lost you for the last maybe 30 seconds of your explanation.
Yeah,
so
sorry.
If we can backtrack and come back to this, that would be great.
Yeah, maybe I give a short answer. In most cases, it's a combination of different methods. Because from my point of view, today we don't have a holistic method that fits all our demands, especially if you have systems with several subsystems that have to be reused. We have to do it in a different way of working, or then then we have a system with start on scratch. So we need different methodologies, and normally we have to combine them for the specific problems.
Okay, very good. Well, I think you're raising a very important questions, and there's one. You see, the title of this session is System Design Tools, and for me, what is clear is that system design tools are still in their infancy. They're still very immature, and what I'm going to ask each one of the speakers and even the audience there is to tell us what they think the next big steps are required, or what are the big gaps and where we should go after this. But this would be at the end of our turn here, so get ready for this. Then now, if we go there, so what are the main advantages of the SSFD over regular SysML diagrams or behavior diagrams? What do you find? Yes.
Actually, I explained that at my another publication, how SSFD compare with other approach, not just SysML. Actually, I explained that actually with SSFD we introduced an established approach here, how you can identify in input output. You have it for every system. You have a lot of inputs, a lot of outputs actually, and how you can identify input outputs, and how you can identify these events between these inputs and outputs. And we also explain how you describe an input in terms of object, or you also have these attributes here, list of attributes. That's why I asked Julian about how you identify high value and lower value, because it's connected to my this SSFD approach. I identify them as attributes here. We introduced this approach actually, and also with SSFD, we also introduce a connection with other tools like FMEA and this FDA interface analysis.
Okay.
This is the advantage of SSFD with other tools in high level.
But is a main hypothesis of your work or your solution, is it that states as an entity is a very, very important property in system design? Is it that we should focus more attention on, or what is your main hypothesis?
It is the hypothesis is that actually in SSFD, I basically link this concept of the state with the flow of energy information. Actually, it's harmony actually between them. But
Okay.
I introduce another definition of how you describe a state here, and I basically connected with the definition of the flow of energy information and material, which is another approach is quite common actually in literature.
Okay.
It's the kind of idea.
Okay. Good. Thank you very much. And now, Stephan, I will let you ask the question to Tommy, because you had an important question there in the chat.
Yeah. Thank you. Thanks for the presentation. At some point, I a little bit was wondering about the things I saw. Maybe I misunderstood something. The first point is a system thinking approach. I know system thinking as a methodology or a methodology approach to get an overview about a problem, to look at a problem from different point of views, to identify as much as possible requirements. And I didn't see this on the slide. Maybe I misunderstood. Maybe you can explain this a little bit more in detail. And then I come to the diagram as a second point.
Yeah, thank you very much for the questions. So you are right that the system thinking is very good at defining or finding the problems and what influencing the problem, and that was kind of the goal in this approach, is to find those leverage points that we need to emphasize more on in succeeding in the project.
Yeah.
And then yeah, it's but we also used system thinking approach as a way of communicating, and I would say that in system thinking, the end result is okay, but it is the process itself that is important, and it's during this process and thinking and collaboration that brings a lot of insights and things that you did not know you were supposed to think about.
Mhm.
Okay. So you split the discussion between the black box view when you come from the stakeholder perspective or something like this, and the white box view inside of the system, if I understood you correctly.
Yeah, so on this level, the abstraction level was very high. We also have more case specifics. So one of the things that let's say we kind of use this diagram as a defined black box, and then we try to attach thoughts and concerns and problems and desired future needs in each of these nodes on the, for example, the systemogram. And then also we could see the relations between the different companies. Okay, like, oh, you have a problem there, I also have a problem there. Or you say you have a problem there, I didn't think that was a problem. And then, yeah.
Okay.
And I have a question. Stephan, are you done? Are you have?
You also can you can also ask your follow-up question.
Yeah, Tommy, what in your presentation you mentioned briefly architecture of the solution or the system, but I did not see it in your presentation. What kind of architecture are you talking about, and what kind of language or diagram are you using to represent the architecture?
So the architectural is actually one of the main points of future research, and one of the cases or research that we will do is something called conceptual modeling, which is more of a, let's say, a more iterative, agile approach to developing systems, which is then converted to maybe a SysML. So since this is very early product development phases, we have a lot of different stakeholders, and these stakeholders needs to understand the models very quickly and learn and then resketch everything. So we're thinking about conceptual modeling and then less degree on SysML.
Okay. Thank you very much. That's it. Any other questions for Tommy or any of the speakers about, like I was saying earlier, system design tools? What a phenomenal topic. It's still early in development. To me, when I talk to my research team, I tell them that system design, it's modeling tools are, for me, I'm old enough to have gone through the paper drawings to 2D CAD to 3D modeling to mock-ups and not to digital twin. And that started about 1975, 1980 to 2020. And I wanted to put a year on system design in comparison. I say, well, that's about like CAD systems and PLM system were in 1985. We were just coming with 2D drafting, 3D models, solid models were not functional yet. And my perception is that in system design tools, we're about the same place. And I would like to know your opinion and what you think is the next step. Is that your, do you agree with this statement that I'm making here? And what do you think are the most important steps that we need to take? Christian, yes, go ahead.
Yes, I'm also of a slightly elder generation. And coming from the traditional concept of design theory and methodology, you know, we start with requirements, go to functional considerations, to physical considerations, to layout and detail design. And what we have seen in the development of tools is in a way backwards. I mean, like Clement formulated a minute ago, we started from detail design with CAD models. Then this was a requirement to go to physical simulation in different areas. And the important step, in my opinion, seen from the design theory methodology now is that system design tools may open up functional modeling. But as was said before by Clement, Fortin, it is, as always, exactly this transition between these two levels, physical simulation, which we have in major parts, and functional modeling, which we are about to explore. This still has problems, and that's for me the big challenge. And maybe one more remark. 50 years ago, systems thinking was part of design theory and methodology, and was fitted into it.
Yes.
And what we are doing now is exactly vice versa. I mean, fitting design theory and methodology to systems thinking. So there's not that much new. Thank you.
Okay.
Yeah.
Well, I will ask now, let's see. Tommy, I will give you the first chance to say what you think about this and what you think is the most important steps, other than, of course, well, you can think about your own projects, but take a step back from this. Yes, Tommy.
Yeah, so it's difficult to say one thing because there's probably a lot of different systems tools that is needed and throughout the whole life cycle, some for the whole thing and some for one specific life cycle stage. But I think we should not forget that there are a lot of non-engineers in the industry and outside the industry. So the system tools should be understood and reason and a possible way to communicate to non-engineers as well.
Mm-hmm. Yeah. What I was thinking about this, it was that clarity is one of the biggest goals that we need to aim for. Okay. Lukas, I'm going through the screen here. Lukas, you're next. Tell us.
Yeah. I think that's a very interesting question. Yeah, if we look today, most of the tools which are using focus on very specific tasks, I think. And also, we're using, let's say, for example, SysML models and different modeling environments like Cameo, for example. And we use them for proposals. Yeah, they might not have been designed for. So what we see is that, or where we should go is that we use, well, what we need is that to use SysML in the background and need some interfaces which are missing here. And another aspect, yeah.
Briefly, yes.
Okay, another aspect in methodical predictive development is that we use visual tools often, and in the SysML we have some a bit of visualization, yeah, but yeah, what we need is yeah, more visualization in the society.
More visualization, is that what you're saying?
Yeah, more visualization.
Okay, Stephan, I will give you the chance now.
Yeah. Maybe some brief words, maybe also an extension what Christian said. From my point of view, we still have a gap between the methods and the processes and the models and the tools. Today, a lot of models and tools, from my point of view, are technology driven. For example, also SysML, you can do a lot of things with SysML, but you also can do nothing with it if you don't have a methodology. And I think a very important task for us, and I also agree, Tommy, we also have to include the users of the different models and tools. We should more bring the methods and processes together with the models and tools, because currently we have a lot of, from my point of view, gaps between them, because the people know methodology, for example, from the study, and then when they use the tools, they, for example, SysML, they use it like a paint tool, and that's not the way of working from my point of view. And we should bring the methodologies together with the models and tools, and then we can use the tools, and also, like Lukas said, the combination of different tools more efficiently.
Okay, thank you very much. I will give the floor now to Julian. We have 5 minutes left. Thank you.
Thank you. What I see in systems design is that we often try to make decisions with high fidelity models and simulations, but the data is not there all yet. So it's like the stage of development process is sometimes not clear, and that goes together with the different tools that are there, but they are not really connected. There are high fidelity simulation tools, there are SysML tools, there are process tools, but they are often not good connected enough. And if they would go together, it would be more efficient, to come from a big solution space and go smaller every time and every iteration loop to find the best solution at the end.
Okay, great. Thank you very much, Julian. Unal, what do you think?
I don't have too much time. I'd like to just highlight the most important aspect. We can say a lot of things, connection with other tools is important and other aspects, but when you want to use a tool or introduce a new tool, the most important thing, it should be easy to apply, easy to learn, and you need to also highlight the contribution, actually, how it can benefit to the industry. And after that, we can consider connection with other tools. I also noticed there is a trend of the link with AI approach, actually, machine learning, digital twin, and other things, actually. I think this is quite important too.
Okay. I see, Felician, that you're there. I'm sure you have a word to say. So go ahead. We have time.
Thank you very much. I mean, I think it's a great question, and I've reflected over this question for a long time as well. I think the one thing that's missing, and I think the views that were expressed actually capture all the angles. I was, perhaps reiterate some of the points with different words. So one of the things that I think are missing with a lot of the MBSE, so talking specifically around the SysML modeling and so on, is they don't capture that the rationale. That was the term that was used in one of the sessions yesterday, which I thought was very nice. It's the functional rationale, the way the system works. So I think the reality is that a lot of the models are actually built once the system is designed. So it describes how the system works, and it captures the understanding of designers of how the system works. Whereas what you need with design of a new system is you need to sort of start to use SysML in designing, so getting that design rationale. And I absolutely agree with the fact that, well, that really brings the functional modeling very much into it, because at the minute, what people tend to do is they do the structural view and then you look at the functional view, but designing the system is completely the other way around. Where I have a little bit of optimism is seeing the way people use this. And even in this session, we had some really nice presentations, as well as yesterday I've seen a few, is once you combine system modeling with advanced simulation, you can start to validate the model, because the other problem with MBSE is really you can never check whether it's mathematically correct. And that's one of the problems. So, it's a model, you should be able to check it. With simulation, you can actually start to check it. The big problem that we have is really getting people to be able to use, so getting democratizing the system. And I just want to make a comment, really highlighting the contribution that Stephan's paper is making, because what I think that this stereotyping of models for reuse is really playing a big role in productivity. And
Can I just announce that I have to say only that 17:30 the closing stage is starting. So please.
Yeah. Well, thank you very much. I think we haven't. Thank you, Robert. Thank you very much, all the speakers, and I think we haven't. We could continue for a good half hour, 1 hour on this topic, which is extremely important. So thank you very much, all presenters, and congratulations again for the best paper. There was some of the best.
Thank you.
I'm really looking forward to see you guys in the future. Thank you very much for participating.
Thank you very much. Bye.
See you guys. Bye-bye.
Yep.
Bye.
Thank you. Goodbye.